Welcome back to the video series. In today's video, we are going to have a look at the particle in a box situation, which is a bound state in quantum mechanics where the particle is free, but it's only free to roam inside a box. We're going to have a look at eigenstate, what those mean in the context and how to implement them in programming-wise, and that's the plan. If you like the video, then please like it, share it, subscribe, and comment in the sections so that we can have more people see these videos as they come. Now, last time I gave you the exercise to try to configure using the parameters of the last video to set the potential to be 10 outside of 0, 1 and place a Gaussian inside this kind of box that we get and evolve and see what happens. So that's the first thing we're going to do. I'm going to borrow the code that we wrote last time, because that worked very well. So here we are. I also need to import, of course. Import confit as cf, import numpy as np. So let's just start simple here. So we are creating a system, here we're going to evolve it, etc. So we're going to set the qm.vxt equal to 10, but it's only going to be 10 outside of, so it's only going to be 10 outside of this region. I'm actually going to use some other parameters here. So I'm going to use between -10 and 20. So have it in the middle. We want it to be 10, but we only want it to be 10 outside of the region of x between 0 and 10. So I'm going to multiply with qm.x smaller than 0. And how do I do this? I need to figure this out. So let me see. So we have, let's just create this object. Qm.x smaller than 0 will give me something that's true everywhere. I cannot multiply with qm.x bigger than 10 because that's gonna give me just, because that I think is going to give me false all the time. Yeah, it's because it's never both of those. But if I add them together, I get something which is, so here I'm getting like the places where it's smaller than 0 and also the places where it's bigger than 10. And so this is the region where it's not. And so if I multiply that with 10, then I should get exactly the profile that I want. And to see that, I could do like qm.vxt is equal to this, and then I can plot that field. So qm.plot field vxt, and then just extract the fig to see it. And here you can see how that potential looks. Vxt is not defined. No, it's not, because it's contained in qm.vxt. So here you can see the potential that I'm inserting. It's 10 outside, and then it goes to 0, and then it goes to 10 afterwards. I don't think dx is supposed to be 0.2 here. I think I want it to be the default value. We'll have a look at that. Okay, so now I have the potential. And I have placed a Gaussian. Well, my Gaussian now is placed central at here. So I'm actually going to put it in the middle, so at 5, and then give it an initial velocity of 1. So let's just try this and see what happens. And I'm also going to create one where I am evolving for longer and speeding it up by a factor of 10 just to see what happens. Let's have a look at the pictures so far. Okay, so it's C. Yeah, we're not seeing the potential in here. So I'm actually going to also plot the potential in here. So what I had the way to do that is that I need to specify that I also want to plot the potential inside here. So qm.plot field qm.vxt, and then I need to specify that it's in the same axis. And the thing about this now is that if you look at the, okay, let's have a look at the animation here. So you can see that the sort of wave packet that we've placed inside the region is hitting the wall, and that's essentially what we're going to be seeing in a minute. But the top of this wave function is at 0.6. Now, if I add the potential here, which is 10, in the same plot, it's going to completely dominate the plot. So I need to, just for visualization purposes, I'm going to divide by 10 so that the maximal value is 1. That's going to make for a very nice figure, and we can see how that works. So let's just see if our plots make sense. This makes a lot of sense, right? So here you can see the sort of initial wave function having hit the wall. It actually looks to be moving quite fast. So I don't know how good this animation is going to be. Let's try also one where we don't evolve it for so fast. So let's do like 2 time steps after this. Okay, so now this the simulation is done, and we can have a look at how it looks. And what we see is that, yeah, so we're starting with this wave packet inside the box. It's hitting the wall and it's getting reflected. But as you can see, after a while, it's sort of bouncing back and forth, and at some point the simulation goes crazy. And the reason that the numerics break down after around like 60 time steps here has to do with the fact that this sort of external potential that we're adding here is a very, very sharp potential that goes like very abruptly from 1 or from 10 to 0 and then back to 10 again. And that causes this kind of oscillatory, unstable motion outside of the region, which eventually takes over the problem. But that's okay. We can sort of still see what's happening inside here, which is the most important part. So that was the exercise. So now let's look at the topic for this video, which is the particle in a box bound state. So we call it a bound state because there is now an external potential, namely Vx, which is non-zero. So just to remind you, when we looked at the first video, we looked at the wave equation with fixed boundary conditions, and we saw that it was like a sine wave which went up and down inside that. Now the particle in a box in quantum mechanics is actually quite similar to that situation, namely that you have fixed boundaries, or you have an external potential, and at the end of that potential, it is supposed to go to infinity. Now, we've set infinity to be equal to 10 in our simulations, but the point is that the particle or the wave function will be 0 at those points, and that causes that kind of mode structure. Usually, when one discusses bound states or systems in quantum mechanics, one refers to what we call eigenstates. And so essentially, there's a lot of good analytical calculations that can be done using to look at eigenstates, but we're going to be looking at eigenstates from a purely numerical perspective. So I've posted this video here by Slackademia, which I thought was very nice, on how you find the eigenstates for a particle in a box. But the essential setup is this, that you have this infinite potential from negative infinity to 0, and then there is a box of length L where the potential is 0, and then at L, the potential goes back to infinity again. Now, in this video, they show how to derive that the so-called eigenstates of this potential is given by this expression here, square root of 2 over L times sine np n pi x over L for n equal 1, 2, etc. And the energy, they say, of this system is pi squared n squared over 2L squared. So what we're going to do now in programming is essentially implementing and showing that these states are eigenstates, and in fact demonstrate that these eigenstates are eigenstates. And what does that mean? So in particular, it means that an eigenstate is a state where if you act with the Hamiltonian on the state, you just get the energy as a number multiplied with that state. And then we're also going to calculate the evolution or the uncertainty in the energy of an eigenstate, because all of those are important quantities. So now the other simulation is done. So let's just have a look at that too. So this is the simulation where I ran the same Gaussian inside the box simulation, but I gave it a slightly smaller initial velocity. Let's see if it shows up here. Oh, here we go. So here you can see how the particle in the box behaves, right? So it's hitting the wall and then it's reflecting back, and at the end you get this kind of oscillatory behavior where the wave function goes to 0 at the edges, which is what we expect. All right, so let's start by implementing these eigenfunctions. So we're going to create a function, eigenstate of, and it's going to be a function of n. And the function that we need to implement is this. So L here is 10, right? Because the length of the box we've essentially set to be 10. So we're just going to use that for the whole thing. Then we need the square root of 2 over L. So np dot square root of 2 divided by L, multiplied by, and then it's actually now guessing the correct answer, but we're going to implement it ourselves, times sine of n pi x over L. So times np dot sine of n, yeah, so it got it, right? N pi qm dot x divided by L. So there's that. So now with this, we can take our quantum mechanical system, we can take our function which creates eigenstates, and then we can set the qm dot psi equal to the eigenstate of 1, for instance. And then we can plot this wave function qm dot plot complex field qm dot psi 0, and we don't need a title for the time being. So let's just have a look. Oh yeah, we didn't return anything, so we need to return this. Right, so this is how it looks. Now, this looks quite strange because, of course, we don't expect the wave function to be have anything here, to be non-zero here. And that's because in this expression, we forgot that we were supposed to only have the sort of inside region here. So the way to do that, I think, is just to specify that the box is equal to qm dot vx, qm dot x bigger than 0, but also that qm dot x is less than 10. So this is our box. And so we can, before returning, we can return this with the box. And if I do that, then we see that I get a wave function which is just 0 everywhere, and at 0 it goes up and then it goes down again. So that's nice. That's the eigenstate. We also have the eigenvalue, or the energy of this state, which is given by this expression here. So def eigen, or energy, of n is equal to, let's just use L equal 10 here. That's what we're using all the time. And the expression is pi squared n squared over 2L squared. So np dot pi squared times L squared. Was it L squared? No, n squared. divided by 2L squared. Like this. So let's just print the eigenenergy. Also, let's just create state number as a variable so we don't have to rewrite that all the time. Print energy of state number is energy of state number. So we get 0.04 whatever. And we can also show the figure by writing qm.show fig. In that case, I need to add fig x to this. Then we can see. The result as well. Right. So that's how to visualize them. Now we want to demonstrate that they are eigenstate, which means to demonstrate that if I act with the hbar onto psi, then I get this thing here. So what I need to do is I need to implement the Hamiltonian operator. Now, we actually implemented the Hamiltonian operator when we implemented the Schrödinger equation numerically. So I'm going to go back to this script here, where this was the momentum operator. So here. So in this in the last video on the Schrödinger equation, we implemented this operator here in the time derivative, and this is actually the Hamiltonian operator. So I'm just going to copy this from there, and then I'm just going to define. Yeah, we don't need this now. Yeah, let's just copy this down here. I don't need this for the time being. We're going to define h hat of psi, and it's essentially going to be the thing that we had in the last video. So this part here, like so. And so what I want to demonstrate now is this that these psi fields are actually eigenstates of the Hamiltonian operator. So what I'm saying is, if I act with h at onto psi n, it's going to give me just the energy multiplied with psi n itself. So what does that look like? Okay, so let's just take, we have qm.psi. We know that it's an eigenstate of this thing here. So we're going to create a figure here, axis equal to qm.plot subplots 1, 2. And then on the left-hand side, I'm going to, yes, so it got it, right? So on the left-hand side, on the first axis, I'm going to plot qm.psi. And on the right side, I'm going to plot h hat applied to that operator. So let's see what we get. And it thought I wanted a field here, but the operator is still a complex field, so that's why it looked a bit strange. But this is what we get, right? So we have the initial state. I can actually also, and then I have after applying h. So on the left-hand side, we have actually, let's put them underneath each other. Is that better or is it worse? No, I think that's worse. So on the left-hand side, we have the initial state, right? And afterwards, we have the state after having applied the h operator to it. And what we see is that this kind of shape here, the wave function, looks exactly the same, only it has a very much smaller value, right? So you can see the top here is only it's only 0.022, whereas originally the top was 0.46, which means that it has been reduced by a large factor, but the shape is the same. The only difference is these things on the edge here, and that has to do with the fact that at the edges, this sort of initial wave function just goes directly to 0, and that causes a very sharp gradient in the wave function, which numerically doesn't make sense the way we have implemented it like this. So the way to get around that is to instead of creating the eigenstate and then calculating the and multiplying by the box, we can just calculate the eigenstate as if it exists for the whole region, and then apply h to the whole wave function and only plot the region that we know we're interested in. So I'm going to do this. I'm going to remove this box, and then I'm instead going to plot just plot the regions of the wave function that we're interested in. And when I do that, we see that we get exactly what we expected, namely that after applying the h operator, we just get back the same exact function, only now it's scaled with some number. And you might ask, what is that number? Well, that number is, of course, the eigenenergy of the state. Let's have a look at the second state. So also let's print the energy of the states. So state number 2. So here you can see the initial state for this is the initial state, and here is the state after applying h. Again, you see that it looks like the same thing, only now scaled by a number en. And in fact, we can show this because we can print the relation between those. So I can do print this new function here. We can print h hat divided by qm psi. And I'm also going to multiply by a box because that's the only place I'm interested in. And as you can see, the ratio between this function after applying h hat and the initial function is just this constant number 0.193554, except for this 1 point here, which is 21, and that has to do with like the numerics of calculating the derivative very near the 0 point here. And this is in fact the energy of the state. So we can go back to state number 1 again. The energy of that state is 0.493, and again, if I take the ratio of this function here to that one, I get 0.0493 almost. So that's how the eigenstates work. If I go to state number 3, for instance, then you see the same kind of pattern, namely that the initial state is this. After applying h, you just get this thing here, and you see that this kind of wave periods that you have here, they are very similar to the waves that we had on the wave equation with fixed boundary conditions. In fact, it's actually almost exactly the same, because what you're looking at in the middle here is a function where the phase is pi, which means that this is just a negative number. So we have positive, negative, positive. So it's like a sine wave that goes like this. Okay, so that's that. And then also we can calculate the variance. So remember in the the variance, or the standard deviation, the uncertainty in a variable, is the expectation value of the expectation value squared minus, or the expectation value of the operator acting twice. I'm just going to show you the equations. I'm going to write them up. So instead of trying to say it out loud. So remember that the expectation value or the uncertainty in a variable is given by the expectation value of the variable squared, or the square of the uncertainty minus h squared. So that's what we're going to be calculating next. And so what we already have some of what we want. So I'm going to calculate hat qm.psi, and I have to apply this. I have to apply this twice, and then multiply by the conjugate of qm.psi. And then I need to integrate this whole thing. And I'm only going to integrate inside the box region. So I'm going to do qm.calc integrate field here, and the region is the box. Just to see that I get a number. Okay, I get a number, great. And then I'm going to subtract the same thing, only now only applying h hat once, and I'm going to square this whole thing. (0.24). I was expecting 0. So why did I not get 0 is my question. Maybe it has to do with...
5 minutes later.
Okay, all right. I've made some changes, and I now see the errors. The error here is simply that I forgot to remove this, that it was supposed to be psi inside this here. So that's just like it only worked. It only worked when I took h out of qm.psi, and now it works. So that was frustrating. This is what happens when you do numerics. So I fixed the error, and now you can see. Well, actually, exactly. So now you can see that so here I'm calculating the expectation value of the energy as just the integral of conjugate of psi multiplied by h hat acting on psi, and then the expectation value squared as the conjugate multiplied by h hat twice on qm.psi, and then I'm printing the expectation value and the squared, and then calculating the variance. And the uncertainty is the square root of this variance. So you can see the energy is 1.35. The expectation value that I calculate is this. And here you can see that which is supposed to be equal to this, but that's a matter of resolution. And then the energy, it's the energy squared expectation value, really. So the value of that is this. And then if I calculate the variance, you see that it's essentially 0, which means that for this eigenstate, the expectation value or the uncertainty in the energy is 0, which is what I wanted to show in this video. So now let's go on to look at the time evolution of the eigenstates. So we know that the evolution of the Schrödinger equation, or the Schrödinger equation, tells you how the wave function evolves according to this equation. dt psi n is equal to minus I, and then this thing here multiplied by psi n. Now, we know that for the eigenstates, when we act with this h bar onto psi, it just gives a number that scales the wave function en, right? So I can replace h bar by en, and then I get dt psi n is equal to minus I en psi n. And this equation here is actually very easy to solve using just normal methods. We're not going to do it here. You can look it up. But essentially, the solution to this equation is that psi n just evolves according to the initial wave function at t equals 0 multiplied by this factor e to the minus en t. So what does that mean? So let's just start looking at this sort of initial wave function here, which is between, so the wave function is between 0 and L. And here we have infinite potential on both sides. Now, as time goes on, this part of the wave function does not change. The only thing that changes is this e to the I-E-N-T. But as we remember from looking at complex number, this is just a complex number with an amplitude of 1, but with a phase that's changing. And so we're multiplying this real sine wave function with a changing phase factor here. So essentially, it's just the color, it's just the phase of the wave function that's going to change, and it's going to change from in the negative direction. So it's going to go from 0 to minus pi to and so forth back on. And it's just going to change like this through all the colors and go back to red again. And so the question is, at what point do we get back to the original phase? Well, we get back to the original phase when the argument or when ENT is equal to 2 pi, because then we have e to the minus 2 pi, which is just 1. So the time it takes is 2 pi over En, which means that if the energy is higher, if we're looking at higher energy states, then it takes a shorter time for the eigenstate to sort of go through all the phases before returning to 0 again, which means faster evolution. So let's try to verify this behavior. And at this point, we're going to evolve this particle in a box solution with the Schrödinger equation. And that is a very hard thing to do because of this sharp edges that we have at the edge of the box, as I mentioned previously. But we're going to do it either way. And just remember that I've spent some time figuring out how to get the correct parameters for this to work. So let's have a look at it. Yes, all right. So let us take our kind of situation here. And we don't need to show the expectation value, nor this, not this, not this actually either. But we need to set this thing here. Also, another thing is that the evolved Schrödinger method, it relies on knowing the state, that it relies on both psi and the Fourier transform of psi being specified. So it's not enough just to specify qm.psi. We also need to specify qm.psi-f equal to the FFT of qm.psi. So now we're ready to roll. I'm going to take it like this. And we're going to use a value of dx equal to 0.5. And we have the eigenstate here. We have the eigenenergy. And we're going to do eigenstate of number. And I also need to specify that I want this to be inside the box. Right. So for n in range 100, we are going to print n just to watch it go. Fig x equal to qm.plot complex field. Exactly. We're going to save the figure. And I also want to show the potential. And yes, we save the figure. And then we evolve the Schrödinger equation. And I'm going to evolve the Schrödinger equation for 13 time steps because I've found out that that's useful. And then we're going to make the animation. So let's run it and see if it works. It's running. We are producing images, I think. Did I forget to Yes, I forgot to set the external potential. So I need to set the external potential, because if not, it's not going to work the way I want. All right, let's have a look. It's very high because I forgot to scale it down by 10, of course, for it to be visualized in the same plot. Now I think we're good. Right. Right. So here we can see the evolution of the wave function, and as we expected, it kind of has the same behavior. It goes from 0, and then the phase is 0, and then it goes to negative, and then to yellow, and then goes back to 0 again. So you see, it's the phase goes from 0, and then it goes sort of negative, and then it turns into teal here, and then it goes further down, and then it approaches 0 again from behind. Now, obviously, ideally, we wanted this to be a very like smooth kind of operation where it sort of kept its shape perfectly and then went through all the phases. But in fact, what we're seeing here is the result of this this kind of numerical approximation where the walls are very sharp and the function is defined to go to 0. But in fact, since it's not since we don't have perfect precision, it's going to create this kind of wavy behavior. This is going to look much nicer in the next video, where we're going to look at the harmonic oscillator, which actually has like a continuous potential for the whole region. Let's also make a simulation for the second state. And we don't need to run that as long. We only need to run it for a quarter of the time, actually. So let's just do that. And the reason, of course, is that the time it takes for it to go through this whole oscillation is 2 pi divided by the energy. So if the energy, and the energy scales as the state number squared, which means that if you take the second energy level, then the energy is 4 times as large, and so it takes only a quarter time to get back to its original state. So how does that look? It looks like this. So again, we see that it started out with the initial wave function, which was just like this double peak second state, and then as it evolves, it just travels through these colors. Again, because of numerics, it's not exactly what we see, but it's almost the correct thing. So I highly encourage you to try to play around with this code, try to evolve the higher states as well, and see what you get. And for the next task, for the next video, I would like you to try to, instead of setting the potential to be infinite or 10 at before 0 and at 10, just set it to this function 0.01 x squared, and then place a Gaussian function inside, and then give it some velocity and make an animation to see how that evolves. And with that, I will see you in the next video.